Let's start with another topic of the course numerical analysis and computation, and this time the topic is Newton-Raphson method to solve system of nonlinear equations. So we are going to have n nonlinear equations. So we will be having n functions on the left hand side which will involve n independent variables. To find the solution set x of x1, x2 up to xn which will satisfy all these nonlinear equations simultaneously, we have to apply Newton iterative formula which is derived as this. So the solution vector at the current iteration will be equal to solution vector at previous iteration plus this y thing at previous iteration. This y is computed as negative Jacobian of x at previous iteration, Jacobian inverse, and then f at previous iteration. And of course, what are these Jacobian and f? F is going to be a vector which will contain the function values of all the function at some x. And this vector is going to be a column vector, so we are putting transpose at the top of it, while the Jacobian will contain the partial derivative of all the given function with respect to all the independent variables. So the first row of Jacobian matrix will be like partial f1 by partial x1, and in the first row you will see in the numerator it will be f1 only, and in the denominator all the independent variables. And of course these values are computed at x, at some vector x, solution vector x. So to start the algorithm, this solution vector will be the initial guess. And in the second row you can see there is f2 in the numerator, and in the denominator all the independent variables, all the x values. And of course this is going to be a square matrix of n cross n dimensions. The stopping criteria will be to compute the vector norm or the norm 2 of y vector yk minus 1, and it should be less than tolerance to stop the Newton iterative procedure. Keep in mind that the convergence of Newton iterative method for nonlinear system is not always guaranteed. So it highly depends on the initial guess vector that we will use. So let's do an example of a nonlinear system to understand this procedure. This example is from Burden and Ferry's book. We have a nonlinear system of equations, and we are having three nonlinear equations which involves three variables x1, x2 and x3, which are enough to solve these three nonlinear equations simultaneously. We have to use this thing as our initial guess vector, and we have to apply the Newton iterative method. Okay, first of all, I have to write my big F. The capital F is going to be the vector which will contain all the small f's. So my this function is f1 on the left hand side. This complete thing is f1. This is f2 and this is f3. So the capital F will contain all these f, and capital F is a vector. You can see from here that f1, f2 and f3 are these functions. Okay, let's compute the Jacobian. The Jacobian will be the matrix which will find the partial derivative of all the f with respect to all the variables x1, x2 and x3. So these three came from partial f1 by partial x1. This is partial f1 with respect to x2, and this is partial f1 with respect to x3. Similarly, this row is for f2, all the partial derivative of f2 with respect to all the variable x1, x2, x3, and this is for f3. So this is my Jacobian matrix. Now to start the first iteration, I have to gather my basic ingredients, which is going to be my bigger function at this x naught initial gas. So my bigger capital F is something like this. So I have to compute all the F1, F2 and F3 at initial gas vector. So I have to put the value of x1 0.1, x2 0.1 and x3 minus 0.1 instead of x1, x2, x3 here, and I will get some constant number. After putting all these values, I will get this vector. This is f at x naught, zeroth iteration. This is capital F. Similarly, I will compute the Jacobian at the initial gas, and I will put all the values x1, x2, x3 where required to compute the Jacobian at x naught. So now all these values are numbers. To perform the first iteration, I have to compute y naught. Let's come back to our previous slides. You can see from here I need the y at y naught, and then I will add x naught and y naught to get the x1. To compute the y naught, I have to do the Jacobian inverse of x naught negative times f at x naught. So after doing this, after finding this y naught from this equation, like negative Jacobian inverse of x naught multiplied by f at x naught, I will get my y naught, and at the end I will add these x naught and y naught to get my x1. So this process will be repeated again and again by putting k is equal to 2, 3 and 4 in the main equation. I will get all the answers, and finally this is the iteration table. So in the first iteration, these are my x1, x2, x3, second iteration, and after doing the 6 iterations, I will see that my x1 is 0.5 and x2 is very close to 0 because it's 10 raised power minus 11, and this thing is minus 0.5235. So this is going to be the solution set x1, x2, x3. And if I see the vector norm, so it is basically 10 raised power minus 10. So I have my answer correct up to 10 decimal places. Now let's develop the MATLAB code of this Newton-Raphson method for system of nonlinear equations. To develop the MATLAB code, keep in mind that we have to develop the code separately for our number of equations. Like for two nonlinear equations, we have to write the script separately, and for three equations, we have to write it separately. So I'm going to develop this code for three nonlinear equations, and I'm going to solve the question that we practiced in this example. To introduce my three nonlinear functions, I'm going to take the help of MATLAB symbolic library. The reason behind this is because I want to compute the derivatives, partial derivatives of these functions using MATLAB built-in library instead of writing the derivatives on my own. So to calculate the derivative, I should take the help of MATLAB symbolic library. So I have three variables involved in my three nonlinear functions. So I'm introducing the first function with f1, f2 and f3. All the three functions are depending on x1, x2 and x3, and I wrote the functions on the right hand side just like they were in the question. Okay, next I'm introducing my initial guess factor for all the three initial guesses, which were like 0.1, 0.1 and minus 0.1 in the question that we solved. And tolerance for stopping criteria, I'm using 10 raised power minus 8 tolerance for stopping criteria, and also the number of iterations I'm gonna perform are 10, let's say. Okay, the next step is to compute the partial derivatives of these functions and also making the Jacobian matrix and the capital F vector. To compute the partial derivatives, if I'm differentiating f1 with respect to x1, I should write di double f, and I am differentiating f1 function comma with respect to x1. So it will differentiate f1 with respect to x1 and store it in f1 x1 variable, which is also depending on x1, x2 and x3. So similarly, I will differentiate all the f's with respect to all the variables x1, x2, x3. So this is how I will differentiate all the f's with respect to all the variables. So f1, x1, f1, x2, f1, x3. Here you can see I am differentiating f1 with respect to x1, x2 and x3, then f2 with respect to x1, x2 and x3, and then f3 with respect to x1, x2 and x3. Next step is to introduce the loop in which I am going to perform the iterations for I varies from 1 to n, and in n we have total number of iterations which are 10, so it will perform 10 iterations. Inside the loop I will compute the Jacobian matrix on current x values and then capital F vector. You can see from here the capital F vector at current x1, x2 and x3 values. To start the loop, I should use the values of initial guess. And in the Jacobian matrix, I will compute all the partial derivative at the current x, which is my initial guess for the first iteration, obviously. So here I'm going to introduce the j and f. So for f, you can see I have uh, a vector f, capital F. Inside the vector, I am computing f1 at x first value, x second value, x third value. What is x? X is my initial guess vector. So x first value, x second value, x third value. I'm not writing the x instead because it will not accept it. Because whenever we call the function, we tell it that what are the values of those variables instead of I am sending a complete variable. So it will not automatically pick the values from the vector. So we have to mention that for the first variable which value I'm going to use, for the second variable which values I'm going to use. So I have to send the numbers for each value of the variable. So I'm computing f1 at x first value, x second value, and x third value, then f2 at x first value, x second, x third, and then f3, all those values. Now for Jacobian, because I have f1 x1, which is the partial derivative of f1 with respect to x1, so I'm computing this very partial derivative at x first value, x second value, and then x third value. Similarly, I computed all the partial derivative at the current x. Since the Jacobian matrix was very long, so I used these three dots to continue the statement in the next line. So in the iteration, whenever I will have my Jacobian computed at the current x and f computed at the current x, I'm going to find the y, and to find the y I have to write negative inverse of j static f. So there is MATLAB built-in command for this j forward slash f. This will do the same. This will take the inverse of j and multiply it with f in a more efficient way. After this, I will update my x vector with what? The previous x plus y. Now in the next iteration, whenever this f and j will be computed at x values, so it will use the latest values of x now. Let me run this code and then we will discuss another issue with the code. So I saved it with the name Newton 3 equations and let's run this code. Okay, you can see that I run this code I ran this code, but it is taking very much time to compute the x. It's just computed the first x, and now it is taking time. The issue with this is that MATLAB symbolic expression take more time whenever we evaluate some value. So instead we should use the function handle command. But the issue with the function handle is that for function handle we cannot compute the partial derivatives. So for partial derivatives, to compute partial derivative we should use the MATLAB symbolic expression. But to compute the function values we should convert this symbolic expression to the MATLAB function, which is basically function handle. To do so, let me pause this for once and quit debugging. Okay, we are back again. So now our task is to convert this symbolic expression functions into function handle. To convert the symbolic expression into function handle, we will use the simple command of MATLAB known as MATLAB function. So I'm converting the original f1 function into MATLAB function handle and now storing it into f11 and f2 I'm storing it into f22 and f3 into f33. So in the capital F, I should compute these function values at the function handle instead of that symbolic expression function. Similarly, I have to convert the partial derivatives, the variable in which the partial derivatives are stored, into function handle, and I'm going to do it by using the same MATLAB function command. So now here I converted the symbolic expression of partial derivative f1 x1 into MATLAB function handle, and now I'm using the variable for it is f1 x11, so that the variable name does not overlap with the previous variable name. So I converted all the partial derivative symbolic expressions into MATLAB function handle, and so in the Jacobian I should use these function handles. So they are in x11, x22 and x33. So I have converted all the symbolic expression functions into MATLAB function and using the MATLAB function handle to compute the values at the current x. So let's run this code now. So I ran this code and the answers are coming quite nicely and in lesser time. In just few seconds, I got all my x values, and in the last iteration my x vector is 0 0.5, 0 0.000 and negative 0.5236. Let's match this answer with the already available answer in the book. So you can see in the fifth iteration I have 0.500 and this is obviously 0. It's 10 raised power minus 11. So up to 11 decimal places it's 0, and this is minus 0.5236 if I round it off to 4 decimal places. So I'm getting the same answer. If you want to see more DPs, so you can use the format long command here and then run that code again. Here, one thing that is missing is stopping criteria. So stopping criteria I should use whenever I get my k. I should check the norm whenever I get my y, sorry, I should check the norm of y and it should be less than tolerance. To calculate the norm 2, there is built-in command of MATLAB which is just the norm. It will calculate the second norm. So norm of y is less than tolerance, then I should break this loop, and before breaking I should display that the answer came in how much iterations. So I just use the fprintf command, so solution found within I iteration. So let's run this code again and see up to 8 decimal places The answer came in 5 iterations. Solution found in 5 iterations. You can make this code general by just using the input commands at the right hand side instead of using these functions, or you can introduce your three nonlinear functions here and your initial guess vector, your tolerance, your number of iteration, and this code will work for your system of nonlinear equations too. But your nonlinear equation should be 3 in number. For 4 nonlinear equations, you have to write the script again. That's it. That's all about Newton-Raphson method to solve system of nonlinear equations. See you people in next video. If you are new on this channel, please hit the subscribe button and do share this video if it's helpful. Thank you.